All right, folks, here is a lesson on a recap on today's lesson right over here. Okay, so this is basically an extension of what we learned yesterday. Okay, so let's start easy right here. Okay, let me take this. What I'm going to do is I'm going to take this. Okay, and I'm going to copy and paste it here. And let's say I do f prime of x equals to d over dx of this right here. Okay, and let me superscript this. Let me subscript that. And if you have this right here, these two cancel each other out. Okay, there's an undoing effect. The derivative of the antiderivative, this gets canceled out over here. Let me go blue here. Okay. These cancel each other out. So f prime of x is essentially g of t. Okay. So if I go one more over here, one more level, I can say this is g prime of t. Okay. Sorry, I meant f double prime here. Okay. So regular f no prime is this is how I want you to conceptualize it. Regular prime, regular f of x is right now at this level. I'm going to call this, okay, let me actually go like this. I'm going to call this the first floor of a building. I'm going to call this the second floor, and I'm going to call this the third floor. Okay, at the first floor of the building, it's f of x, which is the area of the graph of g. So this, okay, excuse me, this is the graph here. Okay, and at the base on the first level, f of x is equal to the area here. Okay, it's the pink. All right. Now, when you take f single prime, okay, the first derivative, remember you also take the derivative on this side, and this has the derivative and the antiderivative cancel each other out, and you're left with g of t. So if this was the area bounded between the graph of g, which is the green, the area bounded by the green and the x-axis, which is the pink, then when these cancel each other out and you're only left with g of t, then it's not the area anymore, it's the function itself, which is the green curve and lines. Okay, so on the second floor, when you take the derivative, you just get g of t, which is not the area, which is the curve itself. When you go to the second floor and take the double derivative of f of x, you get g prime of t, which is no longer the curve itself, it's the slope. Because remember, first derivative means slope. Okay, this is first derivative. Okay, first derivative of a graph of the function that's graphed means the slope of the graph, not the curve of the function. Okay, or not the graph of the function. Okay, so for example, if t was 1 here and g prime, and we're wondering what g single prime 1 is. Okay, that is going to be the slope. That's essentially asking for the slope at 1, which is 2 over 2 negative because it's going downhill, which is -1. So your answer for f double prime would be -1. Okay. Now, if they were asking for g of 1, okay, notice it's not g prime of 1, it's just g of 1. Now it's asking you for the curve, okay, the point on the curve, the y value of the curve, so to speak. Okay, not so to speak, that is what it's asking. So let me rephrase that better. At this first floor, okay, first level of the second level of the building, the second floor, this is the curve itself. So if we plug in 1 here for the x value, it's going to give us 1 on the y value that's on the curve itself. Okay, so in this case, your answer would be 1 because it's asking for, we're at the second floor, which is the curve itself. And when we plug in x value of 1, it gives us a y value of 1. That's the point on the curve itself, the y value of the curve itself, which is 1. Okay, so with that in mind, let's go ahead and do these over here. Okay, this is really easy. Okay, let's do first floor problems, so to speak. Okay, f of 2, remember f, there is no prime over here, we're on the first floor. F of 2 means you just plug in 2 over here. So we're essentially asking for the area bounded by the graph of the function between x value of 0 and 2. So we're asking for the area of this triangle here, which is 2 times 2 divided by 2, which is 2. Okay? Now here is the same concept, except it's asking us for in between the x values of 0 and 4. Okay, let me draw that vertical line here better, which is basically going to be adding the triangle and then adding this quarter circle over here, okay, which is 2 plus pi r squared divided by 4. Pi r squared is pi 2 squared divided by 4 is pi. So we get 2 plus pi over here, which is the area bounded between the curve and the x-axis from 0 to 4. Now for this third one, it's asking between 0 and 6. Okay, so let me clearly indicate that it includes this over here. So between 0 and 4 we already solved. Now we have to add between 4 and the area between 4 and 6 into the mix. Okay, and so the way we find out this geometrically speaking is what we're going to do is subtract. We're going to find the area of this square, which is 2 times 2, which is 4, and subtract this quarter circle here. Okay, whoops, let me shade that in better. We're going to subtract this quarter circle here. So square minus quarter circle gives you this remaining pink. Okay, and this is square minus quarter circle. Okay, it gives you that remaining pink, and you add it back to the 2 plus pi. Okay, you add it back to 2 plus pi, and then you get a clean 6 here because 2 squared is 4, cancels with this 4, and you're left with pi here. Pi minus pi is 0, 2 plus 4 is 6. Okay, now here's where things get interesting, folks. Let's look at f single prime 2. Now we're not at the first floor anymore, we're at the second floor. Okay, and at the second floor, we're taking the derivative of f, which means we take the derivative of the integral, and because integral is synonymous with antiderivative, taking the derivative of the antiderivative cancel each other's out, which means we're left with not the area, okay, we're left with the curve itself, okay, or the function itself. So now, if it's asking us, okay, if it's asking for us for f single prime of 2, okay, you can think of it as asking for g, okay? It's asking for g of 2 right here, okay? It's asking for g of 2. And g of 2 is going to be a clean 0 here, okay? When you plug in x into the function of g, it spits out a y value of 0, okay? And over here, oh, let me fix my screen over here. I forgot to do that because it might have an orange tint on it. Okay. Okay. Now, when you so that's the first floor problem or the second floor problem. Let's go to where it says double prime. Double prime, okay, is a third floor, and when f is double prime, g is single prime. Okay, because here g was no prime, and when you take the derivative of both sides, when you increase the derivative level by 1, so this increases from 1 to 2 derivatives, this increases from 0 to 1 derivative, okay, or 0 to first derivative, I should say. Okay, so now we're not looking at the area, nor the curve, nor the function itself, we're looking for the slope of the function. So now it's asking for f at 1, So we plug in 1 here. So what's the slope at 1? We already figured it out earlier. I coincidentally had the same hypothetical example. It's -2 over +2, which is -1. Okay, so it's going to equal to -1. Okay, your second example that I want to go over today is this right here. Okay, let's go. Whoops. Let's go here. Boom. Okay, and let's talk about what's going on over here. Okay, this example here. And let me see if I can just cleanly extract this. I think I can here. Okay. Now, this problem right here can be it's actually simple, but can be confusing conceptually. So let me clear it up conceptually first before we start talking about the procedures. The procedures are actually pretty easy. Okay. The procedure actually pretty easy. So let's say, so it's asking for this, find k so that this plus k equals to that. Okay, now the first thing the challenge with this is just understanding what the heck is it asking. Okay, so what I'm gonna do, I'm gonna clean this up right here and switch this around. Okay, and I'll tell you why in a bit. Okay. Okay, f of t dt, actually I don't even need to tell you why, it's going to be pretty clear. It's just easier to conceptualize this way. Okay, so I just switch the x and the b, and remember, if you switch the upper and lower bound, you got to make it switch the sign, and it goes from positive to negative. So now we have this equation right over here. Okay, we have that equation over here. All right, which is equivalent to what it originally was. Okay, so now let's pretend, well, we're not pretending, we're going to set a, remember this is always constant, okay, a is a constant. We're going to set that equal to -1, and we're going to set this equal to 3. Okay, look right here, -1, 3, -1, 3. And we're hypothetically going to set x equal to, hypothetically 2, okay? 2 right here. So I'm going to go in red, cross out the x, put 2, cross out this x, put 2. Okay. So now check this out. I'm gonna take this, okay, all right, widen it a little bit so that it's easier to see, it doesn't seem as congested. So this should be a perfect overlap, but because they're both blue, I'm gonna move it a little to the left. That should be on -1 for this -1. Okay, your green is 3, okay, and I'm gonna roughly put this at 2 right here. Okay, I'm gonna roughly put that at 2. So now, okay, now if I'm trying to find out, okay, if I'm gonna try to find out the area between -1 and 2, okay, it's going to be, it's going to be this pink, okay, which is a negative area, by the way. It's going to be that pink, which is a triangle, plus this right here, okay, plus that little sliver right there, okay. And so let's hypothetically say, what's the number I made up here? Let's hypothetically say that that is going to be negative. So this whole thing right here is going to be, let me see if I can draw it up top here. Let's say that's hypothetically -2, because this negative area is bigger than this positive area, so the total area stays negative, and that's hypothetically -2. Now, let's say the area from 2, I should have changed the 2 right here, my bad. Okay, the 2, I'm going to go right here, folks. Whoops. I'm going to put the 2 here. Okay. And remember, that's a B that got crossed off. Okay. All right. And let's say the area from 2 to 3, which is this trapezoid over here. Okay. This trapezoid, the area between 2 and 3. So we're going to assume that this has an x value of 2 right here. Okay. let's assume this trapezoid over here, the area, let's see what number I chose earlier. Let's say it is 6 because it's positive, okay? And then don't forget to also, here, let me draw it consistently on top. So this is going to be 6 right here, okay? That is 6. And remember, we're going to slap on a negative here, okay? Now, because of this negative right here, all right? So now, when you solve for this, okay, I hypothetically chose these numbers up so that it will line up with the k value that it actually becomes later on. I didn't show you how to find k. I'm just trust that it's going to be -4. I'm going to explain it in a little bit. So we're solving backwards for this k. Again, -2 represents the area between 0 and 2, which is this negative big triangle, plus the positive small triangle, and that's -2 because the negative part, this negative big triangle, is bigger. And this trapezoid over here, we're going to assume it's 6. I made that up, okay? And it's positive at first because this is a positive. It's above the x-axis, but then we slap on this negative right here, okay? And this k is -4, which is what we're solving for. So this is the summary, folks, or this is the thesis, so to speak, okay? What we're solving for in k is the relationship, okay, between this side from -1 to 2 and its relationship to the number 2 to 3, okay? So the relationship between this zone in orange on the left, okay, and the relationship of that to this is -4. Okay, that's what we're solving for. Okay, so that is what k is. So check this out. I'm going to extend that and say that even if this 2, this red 2, let's say it was a 1 or a 0. So let's say we move this here, this vertical line. Let's say we move it here. Okay. Whoops, let me ungroup that. Okay. If we move that blue line here, and then we expand this, the relationship is going to still be -4. So even if these 2's right here, and here become 1's or 0's, the relationship will always be -4. Okay? So again, the big picture of this conceptually is we're solving for the relationship between the left orange areas, okay, the pink areas on the orange side versus the pink areas on the right orange side, okay? And no matter what numbers the orange are right here, 2 and 2, 1 and 1, 0, 0, the relationship is always going to be -4, okay? So concepts and conceptual understanding aside, let's actually talk about the procedures. Now is the easy part, okay? So what I'm literally going to do here, okay, this is just plugging in, okay? Watch this. This A and this B, okay, gets plugged in here, and we get -1 and 3, okay? And then the X remains constant here, okay? And we're going to find the antiderivative of 8. And now we just got to find the antiderivative, plug in stuff, and solve backwards for k. Okay? So the antiderivative of this becomes this, and the same, because this is the same, also becomes that. And then you plug in, and then now we set it up, we get ourselves ready to plug in the upper bound, subtracting the plugging in of the lower bound, do the same here. And then now when you actually plug in the upper bound, subtract with the lower bound, you're going to get here, this becomes this, and then this with plugging in of upper bound and lower bound, and this becomes this and this with plugging in upper bound and lower bound. And now on both sides we get a cancel between the canceling of that, okay? And then when you just use now the PEMDAS rules here and here and move this over to that side, you get k equals to -4. Okay, that's the first way to do it. Let me show you the second way. I think the second way is actually pretty slick. Okay, either way is going to give you -4, as you can see. Okay, whoops, sorry about that. So now let's look right here. This is -4, that's -4, just to give you confidence it's going to yield the same result. Now, we're going to set it up exactly the same way. Notice that this right here, okay, notice that the first step, the setup, is exactly the same, okay? And right off the bat, instead of doing the antiderivative, we're going to subtract this from both sides, and we're going to end up isolating k and getting that, okay? Now, we are going to flip, okay? Now we're going to flip these two, okay, to become that, which means if you flip the upper and lower bound, you have to switch the signs, okay? And we flip that so that we can use the additive property from yesterday. And let me pull up the additive property from yesterday, which is right over here. I believe it was yesterday. Let me double check. Yeah, let's see. No, it was actually the day before yesterday. Okay, it was the day before yesterday, which was Monday. Yep. Okay, we're going to use the addition property right here. Okay, let me just copy and paste that. Okay, and whoops, whoops, nope, not even that. It was here. Whoops, not even that. Here. Okay, I got way too many windows here. Let me, just so it's not too overwhelming. Let me, boom, save that, and let's open Wednesday up again. Was it Wednesday? I believe so. And let's go here. Nah, it wasn't Wednesday. It was, yeah, well, this will work too. So anyways, this is where we were, okay? And I am going to flip this, okay? Excuse me, I'm going to flip this and then change the sign from this to this. So now all three greens here become that. And the reason we do that is so we can use the addition property here, okay? And I got the orange, okay? And, oh, whoops, I wanted that to be orange. The addition property has the B's diagonally from top left to bottom left, excuse me, top left to bottom right matching up. And that's why I switched it. I flipped this so that top left and bottom right will match up, okay, diagonally, so that I can use the addition property, okay? So now, instead of A to B, instead of this direction, between two, going in this direction, now, but let me just say it this way. So now, with that squared away, I can combine these two integrals, just like I can combine these two integrals now, okay, right here. And I put 3 on bottom, -1 on top, just like I put A on bottom, C on top here. So I combine it into one integral, and now I just take the antiderivative of this, which becomes that, subtract plugging of upper bound with lower bound, and get -4. So the reason second way is slicker, in my opinion, just my opinion, not fact, is because we only have to deal with one integral, thus one antiderivative, rather than over here, we had two antiderivatives that we had to work with. Either way works because either way gives you -4, -4, which again is the relationship, okay, which again is the relationship between, okay, is a relationship between this orange right here, okay, and this sliver of orange between blue and green vertical line, okay? Hopefully that makes sense, folks. Thank you for tuning in.